Hello everyone and welcome back to EE 4775 Real-Time Systems. We're going to talk about interrupts, so let's dive right in. So we are roughly halfway through the modules that we wanted to cover for this term. If you notice, interrupts right there in the center and application 3 both align quite well. So interrupts should be a bit of a lighter topic than the CPU scheduling. So if you need a little extra time to go revisit scheduling, I suggest maybe you go ahead and do that. Some of the concepts that we are going to briefly touch upon in passing to this lecture, specifically around semaphores, mutexes, are going to get more coverage in the upcoming modules, specifically synchronization, shared resources, and then advanced concurrency. We'll wrap up with intertask communication and time permitting, memory management, and reliability. So, path for today, we're going to talk about what interrupts are, essentially that they are some mechanism that allows us to respond instantly to external events or to events. We'll talk about the structure of ISRs or interrupt service routines, talk about how we use them within RTOS or FreeRTOS, and then also some design trade-offs. So, what are interrupts? You probably have experienced interrupts. We all do. You are going about the normal flow of your day or of some particular session, some event, and something comes up and stops the expected or normal operation, normal flow of something, and then must be addressed immediately. So a great example is classroom lecture is happening and all of a sudden somebody raises their hand. That's not a bad thing, right? It's an interrupt is not a bad thing. It is just an external signal that interrupts the flow of the program or the thing that was happening, so a lecture. Hand gets raised, and in most cases, I will say that hand raise forces an interruption in the flow, and that the question that comes up is addressed, or that interruption is handled with, right? It says, oh, that's a great question, we might deal with it later, or let's put that off to the side. It is still a response to that interruption. So, with that said, an interrupt formally is some asynchronous signal. It can come from hardware, it can come from software, and what it does is it stops a normal program flow to do something, right? It's not just an interruption to interrupt. It interrupts because it is requesting something to be done. So, one type of interrupt is timing based. You might say, hey, is that really asynchronous? Well, it is in the sense that it is outside of the flow of the program. So that asynchronous call, this timing call here, could be that, I set a timer. Let's say maybe once something has occurred, I have a timer or I have a background timer running that is, again, independent of the program execution flow, and I want something to happen no matter what when that timer expires. It could be maybe clearing all memory. It could be forcing a soft reboot. It could be doing an analysis to make sure that that certain things are, I'll say, green in the system, right? That basically a status check. There's a variety of reasons why we have timers. Something that we'll talk about. So, what else? GPIO input, a button press. Now, not every button press should be an interrupt, but there are certain button presses that might be more important than others that you want to be captured no matter what. Classic example of this is an emergency stop button. You want an emergency stop button to work no matter what, to interrupt no matter what is happening, and stop the system from doing what it needs to. You could also have some high priority button presses that you want to immediately act upon. You could consider a lot of the vehicles today, the machines that we have today, are quote unquote fly-by-wire or drive-by-wire, meaning that they are operating no longer on mechanical linkages, or signals to control them, but on electronic signals. There are certain signals that might have and that should have priority over others. Basically, the idea here is that you want to reserve very special, high priority things to use for interrupts, and we'll see that throughout this lecture. All right, so what is an ISR? You're going to hear that a lot. So these interrupt service routines. So when the interrupt happens, you have to do something, right? Usually in class, if you raise your hand, you don't just get called upon and then put your hand down. Normally it doesn't happen. There is something to be done after the interrupt is received, right? So what happens is when interrupt happens, the CPU, the thing that is handling all the processing, saves its state, its context. It says, hey, I was doing all these things. I need to save all that, and let me go do whatever you've asked me to do. So it jumps to this special function called the ISR associated with that specific interrupt. You can imagine that there are different interrupts, right? Different possible interrupts, and the routines associated with those interrupts are likely different. So we get the interrupt, save our state, and then we go to the function that is tied to that specific interrupt. After we're done with whatever that interrupt service routine has set to do, the CPU comes back, restores context, and continues moving along with what it was doing. Again, going with the classroom example, middle of a lecture, question comes up, hand raised, answer the question. A lot of times, the lecture picks up right where it left off after the question gets answered. Now, the amount of time that it takes to recover, right, to basically come back in, is really dependent on the complexity of the question asked. In the context here, you could have, in theory, as complex of an ISR as you want, and that is a really bad idea, right? So you can imagine that if you spend a lot of time in an ISR, the function of your system, right, is no longer behaving in a predictable way because you've interrupted that very nice flow that was all set up. So ISRs are really handy, really great, but they should be used sparingly and when absolutely necessary. So, the far right-hand side of this slide here, what we're talking about here is an immediate response versus a polling response. So the idea here is if you have a question in class, you could raise your hand and hopefully get an immediate response. Or you could hope for me or the instructor, whoever in the class, to ask everybody who has any questions. And maybe they ask that, and hopefully they ask that in some repeated frequency. But that's basically the two different options. You can either raise your hand and interrupt, or you can hope or plan that you get polled, that you get asked for that. So the distinction here, interrupts allow the system to react immediately to events. So I press the emergency stop button, and I assume that if it's backed by an interrupt, that is going to be handled immediately as soon as the CPU is able to save its context and get to me. But that is going to be pretty quick. Rather than, let's say that I have a routine that checks every, let's exaggerate this, every second. And it's cycling through. Now you might say, oh, a second, what's a second? You could easily miss, right? If you don't get that timing right on the button, you might be pressing that button a couple times. You probably saw that in some of the earlier applications where sometimes timing seemed to glitch a little bit if the timing was just slightly off. So the idea here is, to minimize the reaction time and basically the overhead. You can imagine that if I constantly ask and poll, hey, did the emergency stop button get pressed? Hey, did the emergency stop button get pressed? Over and over and over and over again. That's a huge number over the whole course of the life cycle of a device or CPU processing time that is essentially wasted asking, do you have any questions? Are you in an emergency stop situation? Is this the case? Over and over again, basically this polling takes up bandwidth. It's not always bad, but that adds up. And so the idea of an interrupt is, especially for things that are very asynchronous, that will not necessarily happen at great frequency, or that happen very rarely, and rarely in the context of the overall system. So rarely could be, seconds or minutes, right? Versus a lot of the tasks that we're talking about, we're talking about millisecond or millisecond level type loops, very different. So again, these are events that we expect to happen much more rarely, but are critical to respond to. All right, question that you should be thinking about at this point is, why isn't everything interrupt driven? So what is the role of an interrupt in a real-time system? So I've already said it a handful of times. They handle high priority events. So you could think of interrupts having a higher priority than any task by default. So it means that if you have an interrupt, it can preempt even the highest priority task so that you get an immediate response. All right. Since our interrupts can trigger our service routines instantly, they are going to help us to make sure that basically any external event that we have gets handled within their deadline. So they're a great tool. So the example listed here, data acquisition interrupt can guarantee a sensor is read at the exact interval required, something that might not be reliable with only scheduled tasks. I would say that this is a pretty, not weak example, but it is, we have gotten much better with our scheduling algorithms and our ability to schedule tasks to complete very regularly. But you could imagine that if you had a acquisition task that was incredibly critical, that you did not ever want to miss a capture, that using basically an interrupt would be a way to guarantee that. Now, you couldn't do this for every sensor. You could not do it for all the time. But if you had, again, something that you absolutely wanted to capture at a specific frequency and interval, basically an interrupt would guarantee that. All right. Reduce latency versus tasks. We basically have a way to bypass the scheduler, right? In the sense that I can, at any time, if I have an interrupt, preempt everything else. If I get interrupted, it doesn't matter the priority levels that are set. It doesn't matter what is running. I will do what has come in through the interrupt. So that means that the amount of time between when the event happens, the interrupt, and action being taken is incredibly small, right? So if there is a task that requires extremely low latency, right, that you have to respond to this task in guarantee that the response will happen in an incredibly short amount of time, an interrupt is the way to go. All right. Now, with that said, you cannot use them everywhere. You have to use them very purposefully, very sparingly. Everything cannot be an interrupt. If everything is an interrupt, you will not be able to reason about the overall system. You cannot have everything interrupt driven. The ability to forecast when events will happen is really hard, especially if interrupts interrupt one another. It really becomes difficult to reason about. So while you can use interrupts for critical events, you should not, every task should not be an interrupt, all right? If I see that in a behavior code, you're not, you will get points taken off because it is impossible to reason about and it's not the right approach. So interrupts are also a limited resource. There aren't infinite number of interrupts. Interrupts are signals, right? And there are a finite number of signals, hardware or software, that exist. So you cannot have infinite number of interrupts. So you should reserve the limited number of interrupts you have on a system for the absolute most critical things that you need. Okay. So let's talk a little bit about latency and response time, specifically interrupt latency and response time. So what is the time between when the event triggers, right? When the button is clicked and the start of the routine associated with it, right? So remember that it's not just the interrupt that happens, there's something that happens after that interrupt, a task or some set of tasks that you want to have done. So really, interrupt latency is that time between when the interrupt triggers and the start of that ISR function. So this is so behind the scenes, what takes time? Well, if the CPU is working on something, right? If the CPU has tasks that it's currently executing, or it has a pipeline, right? So all of that needs to complete or be in a state where it can be saved off. So the longer the pipeline in your CPU, the longer it's going to take to save off its state. So shorter pipelines, or you could have some special interrupt mechanisms help reduce latency. Other things, there are potentials for basically in certain situations, you might turn off interrupt handling. You might be working on something and say, you know what, during this particular block of code, I am disabling interrupts because I cannot be interrupted during this thing. Well, that's going to increase the latency, right? The response time. If an interrupt happens while I'm in one of those blocked periods, tough luck. The system will not respond to the interrupt. This gets a little bit iffy, right? Because you want to use these critical sections that are interrupt free. You want to keep those really short, because then it's basically the longer any critical section that you have is, increases the potential latency to an interrupt. All right. So the last thing is there is also a way to set priority levels for ISRs. More or less, if you have low priority interrupts, they're going to have to wait longer if there's a higher priority ISR already running. So all of these contribute to the amount of time it might take between an event and response to that event. And so all things to consider. Finally, when we talk about budgeting and measuring these things, you want to try to calculate the worst time interrupt latency, right? So usually, again, you're using an interrupt because you need something to be done within a very specific amount of time that you can compute and calculate. So you have to look throughout all your code, right? Because an interrupt can happen at any point in execution. And you need to look at basically, if you look at the things above, are you disabling interrupts anywhere? And again, I know we haven't seen that, but any section where you're disabling interrupts, you need to time that section, right? So if you're doing this within a task, and it's maybe a task where you're operating on data or memory some way, you need to measure the amount of time that you are masking or disabling the interrupt service routine, because that is going to add to your overall latency. Possibly, right? You don't know when an interrupt is going to happen. So interrupt latency is computed in the worst case. So we basically say, okay, I press the emergency stop button. What is the absolute longest amount of time that will occur? Because I don't know where it's going to happen in my system. I have to evaluate the whole system. If the button gets pressed in this absolute worst location here, right as I turn on, again, interrupt masking or disabling, how long will it take? How long will it take to basically switch context into this routine? So, all right. It's not trivial to do this, by the way. And it takes time. Okay. So let's talk about interrupt priorities and nesting. Priority levels. We've seen priority levels when you talk about scheduling tasks, but same thing applies. We can assign priority levels to our interrupts. Higher priority interrupts preempt lower ones, and if there's a higher priority event that occurs during a lower priority one, it will interrupt the lower priority one and run immediately. So works a lot the same way as tasks. nested interrupts. So you could essentially, this idea of if an ISR becomes interrupted by another ISR, is it designed correctly? Have you designed these so that only the really urgent ISRs preempt others? Like if you don't, it can lead into some really interesting spaces. Again, if you start nesting or having ISRs can interrupt ISRs, the complexity of understanding when something will run gets really difficult. So, all right. How should you go about doing this? Figuring out your priorities. Look, critical time-sensitive events should get high priority. Other things, right? Anything that's not critical time-sensitive, lower priority. The other big thing is you should make sure that you don't want multiple ISRs to have to ping pong back and forth between priority levels. If they do, what could happen is essentially they can take over the entire system and starve everything else. So if you have two ISRs that occur rapidly, right, that occur frequently, they probably should also not have both high priority, right? Otherwise, these two rapidly occurring ISRs are going to take over everything else. All right. We don't really see priority inversion in our interrupts. They don't wait on being locked. But still, if you really set up priorities incorrectly, so if you have a medium priority ISR that's running, and then a high priority ISR that is pending but not turned on, it can be really bad. So the point here is that there's a lot of nuanced use of ISRs and sketching out how an ISR works, how long it takes, what priority levels, understanding all the interrupts that you have and how they're being used is really critical to draw out, to write out, because you could get yourself into a lot of mess if using interrupts just, I'll say, without care. Okay. So some basics. Let's talk about these ISRs. An ISR is really just a function. It's a callback that executes to after an interrupt happens. It is just a really small function. It is not a normal task. All right. What happens is, again, the system as a whole saves everything that's happening, executes the ISR, and then comes back to what was happening before, right? So it is really interrupt the system's normal behavior, do this thing, come back to the system's normal tasks. So what does the ISR do? Typically, it is going to clear the interrupt source. So I've been interrupted. Thank you. You can put your hand down, right? So clears the flag. So basically, the interrupt doesn't happen again, right? So this might be less of something you've seen in class, but you can imagine online, perhaps in a Zoom call, somebody raises their hand, asks a question, and then doesn't put their hand down. That is an example of not clearing the interrupt source, right? Because I might think you still have a question in the hardware system here. So I acknowledge the fact that the interrupt came in. I'm going to set the flag low so I don't get re-triggered unless the ISR triggers again, but that's a very high frequency one if it does that. And then what's nice is after I put that flag down, I'm going to do some very minimal processing. Whatever the absolute smallest amount that I need to do to help do what I'm supposed to do. It could be, I might read a sensor value, data register, toggle an LED. I might do something little, minimal processing. And then hopefully what I'm actually doing is I am calling a task or setting something, a follow-up flag for processing in a task that happens periodically. So again here, the goal is to get in, clear the flag, and move on quickly, right? These are quick routines, We're keeping it short. We're doing any of the essential work as quickly as we can. Grab data, reset hardware, then anything that needs to happen that's like, I'll say beefier processing, any real computation, that should be punted off to a task somewhere. Found this on the FreeRTOS blog. With an RTOS, you typically do very little in the ISR. Maybe grab data and clear the interrupt and leave more complicated work for a task. That is really as succinct as we can get it. Some big things here. An ISR cannot block or sleep. It's not a task. It always runs to completion. So the goal is to get in, get out as fast as possible and resume scheduling. So ISRs are little helper functions, right, that do critical work quickly and punt everything else to other tasks. All right. So some do's and don'ts. You want to keep your ISR short and fast. I've said that a handful of times. So the goal here, right, if we're contextualizing it, microsecond scale execution if possible. All right. Don't use blocking calls. So never call a function that might block or take long inside from an ISR. So how to do this in FreeRTOS or RTOS? Only use API routines that end with the from ISR bit. So you'll see there's a handful of blocking calls like that we haven't talked about. We're going to talk about more next week. Semaphore take, task delay, memory allocations, even printf. All of these could block. Don't use them in an ISR. Okay. Do use volatile for shared data. So if an ISR modifies a variable that's also used somewhere else, declare it volatile. All right. It will prevent the compiler from optimizing out reads and writes. Also, prior synchronization. We're going to talk much more about synchronization in the next couple weeks. So we'll talk about that more. You want to have minimal instruction count, right? You don't want to be doing heavy computations or logic in the ISR. You don't want loops, no processing, complex processing. All of that should be in a task. If you have an ISR here as an example, needs to handle 100 bytes of data from UART, best practice is to read them in buffer, then wake a task to process the data rather than parse it all inside the ISR. You really should not be doing any complex handling of data or information within the ISR itself. All right, don't do non-urgent work, right? Your ISR can signal or schedule other tasks for anything that isn't absolutely time critical. So bottom half processing is key. Basically that means is ISR gets in, gets out, and sends everything else down the road for heavy processing later. All right, so here's our example from FreeRTOS. It is related and almost directly from the application 3 here. So ISR safe FreeRTOS APIs. They are usually, the suffix here is from ISR. There are some I think that might have the underscore and some that don't, but basically what you're looking for is from ISR. You never want to call a normal any of the other functions without a from ISR inside of an ISR task function. Actually, I shouldn't call it a task function, routine. So a couple different ways that we can, so the example here is use X semaphore given from ISR instead of X semaphore give. And so that's actually highlighted here on the left in the code. Again, we haven't talked about semaphores yet. Don't worry about it too much. That's why it's not the focus of the application either. We're going to build on that next week. So if we look here, what happens inside of an ISR, we usually unblock and notify the task what task we're going to work on. And ways that we do this is through either binary semaphores, direct task notification, queues or message buffers, all of which we're going to see the upcoming weeks. On the example on the left here, we use a binary semaphore. And so what we see here is we have in our ISR, which is the top function here, we have essentially X semaphore give from ISR, X button semaphore. So we have a semaphore on a button and we are giving it, right? We're giving it from the ISR, and somewhere in a task later on down here, we get an X semaphore take. So this is within the task, takes the semaphore, right? Same one, X button semaphore. So it takes it. So it's given from the ISR, taken by the task. Again, much more on semaphores next week, but you can basically see this pattern here. So that is one common way to unblock the task from doing work. So this task down here was not going to do any work until this semaphore was available to be taken. So that's one way. We'll talk about these other mechanisms in the future. So some great ways that we can minimize overhead. We'll see direct task notification reduces overhead by, well, it looks like 45% faster, less RAM. Again, we'll talk about it more. All right. After all this is done, right? After you have essentially signaled the task to work, right? You then yield. You basically say, okay, I am going to yield my time now. I'm done. So if an ISR wakes a higher priority task, right? You could imagine that this ISR could be interrupting a higher priority task. You want to run that immediately after the ISR. In FreeRTOS, these ISR safe APIs can indicate if a higher priority task was woken. So you can know, basically, when you interrupt here, you are going to get a signal that lets you know if a higher priority task was woken up by doing this. And that lets you yield back to that higher priority task, right, when you're done. All right. So way that I basically show you how you can do that right here. This setup is doing exactly what I just said out loud. All right, what this does is it minimizes latency. Task runs without waiting for the next tick. So you're gonna get in, do your stuff, right? Give this semaphore and immediately release back to the high priority task. So, all right. So a little bit about bottom halves, deferred interrupt handling. This is essentially what we just saw. We split our processing event interrupts into two parts. The absolutely critical part, and then which is what responds, right, and sets everything up, and then the handler task, the bottom half that does the work. And so the application 3 this week is a great example of that, and we'll have another video on that. And actually this example here, the ISR really isn't doing much work. It is handling the ISR, and it is unblocking some other task that is further on. Okay, so this lets you keep your ISR short, lets the scheduler in RTOS do its thing, and so this is definitely the clean way, the efficient way of doing this. System, it becomes super responsive, and you're not hogging CPU. All right. If we continue on, we look at some of the common design trade-offs and pitfalls. Here they are. Pitfall. You have too many or too long ISRs. Why this is bad. Basically, your low priority tasks don't ever get to run. You get a huge amount of jitter and overload. You can look up the Apollo 11 radar bug. I'll put maybe a video on the course so you can see that as well. Quick way to fix this, shorten your ISR. Your ISRs, again, should be super, super short. Lower the interrupt rate. So your interruption rate frequency can be lowered, especially for timed interrupts. And then the one that also really helps, that we've already mentioned a few times, move as much of the work you can to tasks. All right, missed deadlines and signals, why this matters. If your ISR is masking others or fills queues faster than the task's drain, right? So you can imagine that an ISR might fill up data somewhere, but if that data doesn't get processed quickly enough, essentially you get data loss, right? You have one ISR filling, and if your tasks are not taking care of them quickly enough, you're going to get into a problem. So easiest fix is basically getting your buffers to the right size. Basically your goal is to get your buffer to the right length where your ISR is filling them, or the call, whatever's filling them, is also being the other task that is handling the processing or draining of them is balanced, right? So you're never you're never filling the buffer completely. Again, throttling comes down to timing. You might need to slow down how much you're filling your queue, or you need to speed up how quickly you're processing your data. You could also use semaphores, queues that are sized for the worst case. Again, more on that in the coming weeks. Other pitfalls, again, this is motivating future weeks here. Unprotected shared data. You have an ISR and a task that are trying to operate or are operating, unfortunately, on the same variable. You get some corruption, right? You can imagine that your task, if it hasn't blocked ISRs or interrupts, and it needs to operate on some data, and then your ISR comes in and modifies some value, you're going to be in trouble. So the ways to handle this are basically handling it with mutexes. There's other ways as well, spin locks if you have multi-core systems. Again, we'll talk about mutexes and semaphores the coming weeks. No overload plan. This is a common one. Imagine that you have essentially a very tightly packed schedule, set of tasks, and all of a sudden you try to have multiple interrupts. It will cause your system to essentially stall. You will be at overcapacity. You will not be able to complete all the tasks with the interrupts as well. And so you have to, the way to fix this is you have to start dropping or degrading low value work. So you have to ignore or drop tasks, keep only the critical safety tasks running so that you don't reach this situation. Last thing here, hard to debug timing bugs. Interrupts, especially with their latencies and all of the timing things that are happening here, you could get yourself into a race condition. And these happen in very small time windows. So there are ways to trace and look at what's happening. We'll try to build out and show you some of that, hopefully by the end of the course. Okay, summing everything up here for you. Interrupts are incredibly powerful. All right, they allow us to be responsive to handling external events immediately. You can help them to meet the timing requirements, but you have to really use them carefully. And so we're just getting introduced, we're just getting started, but just know that they are not some blanket solution to everything. You can't use them everywhere. When you do use them, we're going to keep them short, simple, non-blocking. Right? You do the urgent part of the ISR, and then everything else you defer to a task. Use the ISR safe APIs, follow the rules. Okay. Integration into RTOS, let the real-time operating system do what it's meant to do, which is schedule tasks. If you interrupt everything, right, all the time, like that's not going to be convenient. So interrupts are used to like wake something up or to signal a task to do something, right? Use it that way, right? Don't use interrupts to do all the work. Use it to enable other functionality when needed, right? And enable tasks is really the way to do that. All right. Again, this will come with practice. It'll come with time and more exploration. You want to assign interrupt and task priorities with purpose, right? Just picking numbers or just setting everything to a high priority or setting priorities without really considering how tasks will interact and what is actually critical is a big misstep. Okay. Yeah. All right. The thing again, it's going to come with practice and time, is your goal is to always consider the worst case, right? What happens if this interrupt happens all the time, right? What happens if it triggers over and over and over again? Will my system be able to continue to respond as expected? Testing and tuning is definitely something that will come, again, with time. It is important. And I will say with that, pretty short, but if you have questions, let us know. If you've used interrupts or if you've seen interrupts in other classes, talk about it on YellowDig, right? What did I miss? Or what do you think are really interesting things that we should talk about? So thanks, and until next time, enjoy.